Okay, one more time. My headphone battery was about to die. That's why I had to stop the last lecture partway through. We're going to look one more time at this preprocessor stuff just to remind everybody what's going on, and then we'll actually look at some of the other. Then we're going to look on to other topics. So let's have a quick look at what we had in pixel image. So pixel image.h, what we moved everything over to. We made two different we have two different CPP files and we have a .h file. We moved our code around so that all of our code wasn't just in one giant file. But in order to do that, we needed to have this include.h thing. So pixel image.h, both of my CPP files are going to include this particular file, and so that way both files will know about some of these things, like for example the pixel struct right here. It also lets us know that there's going to be a function called makeRainbowRect. MakeRainbowRect is defined all the way over in pixelimage.cpp, but preprocessor text.cpp can still use it. It knows where it is because they both have the same .h file. They both sort of the linking at the end will tell preprocessor text.cpp where the actual files, where the actual functions defined. Here we have a bunch of different defines. So I defined what a byte is as a character. It is a character is 1 byte, but I don't want it to accidentally think that a character, when I'm talking about a character that I'm looking at the letter A, I actually want it to think of it like a byte of information, 0 to 255. So an RGBA, red, green, blue, alpha, for transparency, value is actually an integer. It's 4 bytes. I can represent it using 4 bytes. That's all I need. So instead of using some kind of struct, which I've done in the past, I could just have a single integer and then play around with it this way. So let's do an RGBA, another kind of RGBA thing. I'm going to call this struct sRGBA, and that thing is going to have, I'm going to need this byte R. I'm going to need to put that in another part. G and B. Wow, that autocomplete's really a pain. A. All right, and I'm going to move all of that down to a different area. So that is another way I could have defined an RGB value, right? It is a struct with 4 different RGB values, and I could go sRGBA.R, sRGBA.G, sRGBA.B. This way with a define, it's just a different way of solving the same problem. So if I have an RGBA value, it's actually just an integer. If it was just an integer, and let's do that as well. So let's go to let's do preprocessor like we had before. Let's go down to my main function here, and I'm going to find out how big these things are. So in case you're wondering, size of sRGBA, great, and I need the E in size of. So spelling is kind of useful. And this is going to be RGBA, an RGBA structure. All right, and int size 1, int size 2, and I want to see what the heck these values are. So compile it. Let's see what I got. So I'm going to go 2 steps down and then look at the value. So size 1 is equal to 4. Size 2 is equal to 4. They're in fact the exact same size. The difference is I'm letting the struct handle everything. That might be the smarter thing to do in this case, but I wanted to show you preprocessor instruction. So this would be one way of doing it. The other approach to doing this is just say it's an integer, but now I got to do some fancy math. So to get the red value in the RGBA, well, it depends on where I want to put my R, my G, and then my B. So, or let's do the make RGBA first. So I have an red, a green, a blue, and an alpha value. I might want to shift the red 24 positions over. So whatever the value was, let's say it's 32. I would put 24 zeros after that value. This one would be putting 16 zeros after that value. So if this was 17. It would be a 17 in binary with a whole bunch with 16 zeros afterwards. This would be 8 zeros after the number, and this would be just the number itself. Notice if I add a million and 1,000 together, I get 1,001,000, right? They don't collide with one another at all. What this is going to be doing is it's my R value. Let's put it as a comment. So let's do the blue and the green. So the blue might be, if my blue value was 11010011, let's say. If that was my B value, well then what I really want is 11010011 1, 2, 3, 4, 5, 6, 7, 8. That's actually what this value right here is. It shifted it over 8 bits. If I add, and let's say alpha is equal to 1, 1, 3, 4, 5, 6, 7, 8, right? It's all on. It's completely opaque. It's not transparent at all. So if I did this and then I plus 1, 2, 3, 4, 5, 6, 7, 8, there's no zeros preceding it. 1, 2, 3, 4, 5, 6, 7, 8. Well, that's going to be equal to 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. All right. Notice if I've shifted all the bits over 8 positions, shifted another 16 positions, shifted it over another 24 positions, they don't collide with each other. I just have all of the value for red at the top end of my number, all the value for green at the second chunk of my number, the blue at the third chunk of my number, and then the A at the very end. I can store each of those sort of independently and get what I'm looking for. To get the actual value back, let's say I'm taking the blue. Well, I'm only going to be looking at 8 positions in. So I will get the pointer for my RGB value. So it's just an integer. It's a pointer to an integer. And then I'm going to say, no, no, no. It's a byte pointer. Now, if I pretend it's a byte pointer, I could pretend it actually has 4, because an integer is 4 bytes long. I could pretend I have an array of size 4. I don't. I have a single integer, but I can pretend I have an array of 4 bytes. So I can then say, okay, go into position 1 in this. So that would be exactly 1 byte over. This is exactly 3 bytes over. And so I can get to the individual part. I can get to this by going 1 byte over. I get to here by going 3 bytes over. This is the number of bits after all. So this allows me to, I can do some really crazy things. And notice this is really sort of ridiculous to read. I don't want to read this thing. It looks really convoluted, really complex. I fully admit that. But the benefit is I don't need to look at this. If somebody's figured out how this actually works and made sure it's correct, I don't want to be putting something as crazy as this everywhere in my code. That would be insane. But what I would like to be able to do is say, just give me the green value, give me the red value, give me the blue value, and not have to worry about how it's being done under the hood. I just want to just get the value. So I can actually just grab the value for the red anytime that I want. If I go down to here's make rainbow rect, here's my pixel again. Let's have a look at how I could actually get to the individual parts that I'm looking for. So here are our course stuff that we were doing before, and I made a rainbow rectangle. Fine. What if I want to just get this particular RGB color? So what if this is me, I'm going to shift over 244, shift it over 24 positions, and I'm going to shift 100 over 16 positions. That's the same as me calling this function make RGB, where I shift it over 24, shift this over 16, shift this number over 8, shift this number over 0. Color 1, color and color 2 should be exactly the same value. Then if I call get red for this particular color, I should get exactly the color, I should get the same color depending on no matter what version I do this. So let's actually call get red on color 2 while we're at it. So the value for red should not have changed at all from the first time to the last time. It is actually going to be doing the same thing. Get red will be doing something very similar to all of this. So get blue will be doing the same thing as this up here. And notice my color and color 2 I'm going to get the same value. It's just an integer in the end. So they should be identical to each other. This value red should not be changing. Me getting the individual blue component, I could do it this way, or I could just call this function and not have to worry about how all of that stuff is implemented. So am I actually running? I'm going to continue, and let's plop a breakpoint right here. Okay, and I'm going to just stop my, it uh, it couldn't continue without recompiling. So all right, let's do that. And here we go. This is course is taken. I got to do one more. Sorry. RGB value. So right now it's a bunch of gibberish. Well, let's move it down one position. The color value is this. If I actually let's look at it in terms of hexadecimal, because that hopefully will make a lot more sense. F4640000. F4 happens to be 244. 64 is a binary is the number 100. It's 100 in 64 in hex is 100, and then 0000 the G and the B. All right, what I should get for the red, I should get 244 or whatever that ends up being. So F4 when I call get red, and then I should be able to do it again. So next step, our red value is F4. If I convert that back over to, let's say, if I convert it to an integer, it's still going to be considered a char. But F4 is the number 244. If I do it again, nothing should change. It's still F4. I could get the value for blue. That I would expect it RGB. So the second value is a G. Here's my blue. I would expect the value to be 0, then the value 0, then the value 100, which is 64 in hex. So byte 0, 0, and 64. And I could call get blue, and that's not going to change anything at all. It's still going to be the value 0. This is the kind of thing that people actually do if you're making a video game and you need to worry about how optimal your code is. This ends up being just because you're relying on the math and you're not calling extra functions, you're not having a bunch of if statements everywhere. These preprocessor instructions can really speed up your code, and this is actually what game developers will actually do with their code. Also, if you're really worried about memory or anything like that, it's quite efficient in that respect. So if we went back to our original function, our thing here, we were looking at pointers, we were looking at how we could do dynamic allocations of memory, we were looking at program construction, and I wanted to go over a couple more things afterwards. That is casting. We've already talked about casting a little bit, and there's actually two different kinds. We have an implicit cast and an explicit cast. Now, an implicit cast is one where you just say, I'm going to make this an integer when it's actually a character. If it can do the calculations, if I have a long and then I say it's actually a short, well, it might be a problem. If I say it's a short, if it's the variable is a short, like a half size integer, and then I make it a long, that's not a problem. I can implicitly cast it. I don't have to do anything. I don't even have to say it's a different file, different format. Sometimes though, I need to explicitly cast if it doesn't want to do it by default. And we'll only look at really one way of doing explicit cast. There's multiple ways, but the big way that we're going to be looking at is putting parentheses around it. So here would be examples of an implicit cast. The value 3 is an integer, but it's easily able to fit into a short. So the short integer will take that value 3. I could then say, hey, well, it's actually a long. So I'm making a brand new variable. It should be a long actually. So let's put that in there. Long. All right, and I'm going to save that. Full screen it. All right. It could be a long. Great. Well, it doesn't really matter. I can make it a long because I'm increasing the amount of precision that I have. The size of the number I can represent is actually bigger than it was before. Or I could just cast it to being a double. Why? Because I don't lose precision again. However, there's times that I actually need to forcibly do things. So there's an implicit, implicit cast can be dangerous because you assume how the compiler is going to work and how it's going to understand things. That may not be the case. So we've hit cases of this where I do an implicit cast, I have an integer divided by another integer, and then I cast it over to a double. So let's do that as an example. So if I have call it d is equal to, you're implicitly assuming what this thing is actually going to do. I'm taking the integer number 4, dividing it by the integer number 3, and then I'm assuming that, and I'm assuming the order of operations, what var is going to do. I'm going to assert, at least, that for what I'm going to do, for what the compiler is actually going to do in this particular case, is it's going to do 4 divided by 3, giving me a 1, and with a remainder 1. But I'm just going to get the value 1, and then I'm going to put 1.0 into var. I'm not going to put in 1 and a third into var. That's not how it's going to work, but I'm still doing an implicit cast, but when I do that cast is different. So instead of that, what I could have done instead is I could put the word double in front of the number 4. That means it's 4.0 divided by 3. Well, if I have a double divided by an integer, I'm going to be doing double arithmetic, floating point arithmetic. That's going to give me 1 and a third, and that's what I'm going to store into var. By doing an explicit cast, I can sort of control when things are happening. I really don't want to do implicit cast unless I'm pretty positive what's going to happen. So, um, so we can actually do implicit cast in a lot of other ways, but sometimes it can lead to compilation errors. So if you want to make absolutely sure, set it explicitly. That would be an explicit cast, what I have here with the double. This thing right here. All right. So here's my explicit cast approach again. I have the variable I'm going to go to, or maybe not even be assigning it to a variable, but here's me doing a cast. I'm saying this variable B, no, I want it of type variable A. So if I have a floating point number, I say no, it's an integer. If I have a short, or if I have a long and I want to make it a short, no, I'm making it a short. I could cast a integer pointer to a byte pointer like we did in the last example, for example. This is very, very useful, and there's actually multiple ways of doing explicit casts in C, but this is the classic old way of doing it. So sometimes you might get an error, a warning, but if you're explicitly casting, you're saying, I know better than you, I'm going to do it this way. And if something goes wrong, well, something goes wrong. But you chose to do it this way. So here would be another example. I could convert the 4 to a double. I could convert the 12 to a double, or actually it's going to be, let me see, when I count my parentheses. It is going to be casting the 12 to a double, the 4 to a double. That whole thing is in parentheses. It should be... No, the 12 is just by itself. It doesn't matter. But the 12 is going to be 12.0 right here. The 4 is going to be 4.0. I'm going to do my division first. So 4 divided by 12 first. And then I'm multiplying it by 92. If I didn't have this cast here, what would end up happening is I do 4 divided by 12 gives me 0 because it's less than 1. And then multiplied by 92, still 0, and so the value would be 0 if I didn't do this casting. And we've done this a number of times. Every single time we did malloc, we did a cast. We have to say, hey, this is going to be a character pointer. It's assuming we're always going to cast when I use malloc. And so that's something to consider at all times, right? Technically, I could say this is if I wanted to have, let's say, a size of, in this case, 40 characters, I can do the size of an integer, 4 times 10, 40, and I cast it to a character pointer. There's no harm, no foul on this one. I'm just saying this is 4. That's all that resolves to. It doesn't say that it has to be an array of integers. It just says 4 times 10, that I want 40 bytes. Oh, I'm going to make it into a character pointer. I could also then just take this. So here's my character pointer. I'm going to cast it to an integer pointer immediately afterwards. Here's my other cast. And then use it as an integer pointer. And I should have exactly 10. A num list points to a chunk of memory which is exactly size 10. A text points to the same chunk of memory, but it has 40 elements in it. It depends, it's the same chunk of memory. It depends on how I view it. It is a chunk of memory. 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's fix it up that way. And or I could say it's 2, 3, 4. 1, 2, 3, 4. Right? Depends on how I want to view things. If it's an int star, it's a chunk. If it's a char star, it's a whole lot of these little tiny 1 byte slices. It's the same memory. It just depends on how I want to view this thing. If I consider it an array of integers, I get 10 slots. If I consider it an array of characters, that same array, the same number of bytes, I consider it's an array of 40 slots. It depends on the size of what each one of these things is. Okay, so I was going to get rid of this cout statement just because we're not doing couts that often in class. But if I do printf, it's going to do it for me. It's going to change things for me. So here is me using me doing an explicit cast. I put the number 65 in. I cast it to a character. And what am I going to spit out in the end here? I'm going to spit out whatever 65 in is in ASCII. That's the character. I think it's the character A, right? It's not the number 65, it's the character A, and I'm allowed to just sort of cast one thing one way or another. The the binary underneath it all is exactly the same. But casting allows me to say, no, I'm going to interpret it one way, or I'm going to interpret it a different way. All right, so I could take any one of these particular things. So here's my ASCII table for all my various characters. If I went through that ASCII table and one character at a time, I can make a for loop, go count from 0 to 127, and just output each individual character. I would then cast it, but I would want to cast it to a character instead of just a number, just so it gives me the right representation. So, by the way, it's uppercase A, sorry, not lowercase a. 65 is A. If I did, here's a cout statement. I go from 0 to 128 and I do this cast. What's going to happen? I'm going to have non-writable character dot, non-writable character dot, non-writable character dot. The first, God knows how many of these things I have, one after the other. And then afterwards, when I finally start getting to these writable characters like exclamation point, you'll see exclamation point dot, open quote dot, the pound sign dot, dollar sign dot, percentage sign dot, this dot that. You'll just get every single ASCII character one after the other with this for loop, because I'm casting it to being a character. It's not a number. I'm going to interpret it as a character. So I would like you to try this one. If I wanted to write out the first, we're going to write out the letters of the alphabet, but I want to have lowercase a, lowercase b, lowercase c, uppercase c, all the way through all the different characters. So all the alphabetical characters. I would like you to try and write a for loop that does that. And after we unpause the video, you will look at the answer. So you can pause the video now. Okay, so here's what we're going to be doing. I need a for loop. I'm going to start off at position 0, where my A's are going to be, and then I want to go to 1, 2, 3, all the way up. But I also want to offset my numbers here. So what I want is, I have a 65 and I think it's a 97, but I don't want to use those hard-coded numbers. I want to just put in, so 65 and 97 are my two starting points, but I want to do 0 plus the character A, 0 plus the character lowercase a, 1 plus the character A, 1 plus the lowercase character a, and just keep doing that. So my for loop increments by 1. It starts off at 0 and goes to 26. I have 26 characters in the alphabet. And then on top of that, I'm just going to add the character A in front of it to make the math work. So it'll go from 65 to 66 to 67, 68, 69. Right. 97, 98, 99, 100. Here's how we could do it. So I have a for loop. I'm then going to I'm doing a cout statement in this case just because I want to show casting. I'm going to say, yeah, I'm going to interpret this as a character, and it's going to be whatever my index is, 0 to 26, plus whatever the character A is, And then otherwise I'd do a bit, and I'm also going to do the same output, but instead of it's going to be 0 or 1 or 2, whatever the index is or the I value is, plus the character A. So it's going to be uppercase character A. So it's going to be 65, 66, 67, 68, 69, 70. So let's go over some brief errors in code, especially when it comes to compiling stuff, just to remind us what we've been doing. So we actually have 4 different kinds of errors, and they different errors come up because of where they where they pop up in the build cycle. The one that everyone underestimates, that is actually perhaps the harder errors out of the whole bunch. Everyone always thinks compile errors are the worst, right? Because you're just learning to code right now, and you get this compiler error and you don't know what to do. When you've programmed for a while, you're probably even seeing it right now. Compiler errors, you can figure out what the heck the compiler error is telling you, and you can look at approximately where the line is, and you go, oh, I missed a semicolon. That's a compiler error. A logic error is when you did something wrong, stupid, or you didn't think it through. So if I have a for loop, a logic error, if I went back to my previous example, a logic error might be I output the uppercase character A before the lowercase character A. So I just flip those around. Now, everything compiles just fine. It seems right-ish, but it's not actually the correct solution that we're looking for. I was supposed to go lowercase, uppercase, lowercase, uppercase, and instead you went uppercase, lowercase. Logic errors are the kinds of errors when I thought it was right, everything sort of looks right, everything's at least working, it compiles, things don't explode, but the answer's wrong. My logic is flawed. I may not be doing the right number of things. I may not be checking to see if I have a null. I might not be, my values that I'm outputting might be slightly incorrect. These kinds of things, like everything runs, but I get the wrong thing. Compiler errors, when I try to compile it, I can tell you the line of code is wrong. There's some syntax or some part of my code, written code, that's incorrect. A linking error is things like if I've made a prototype for my function, but I don't define it. That would be a linking error. If I left off this paint rect or make rainbow rect function, if I left off the definition of that and just left the prototype around, that would be a linking error. I went to call the function and then it goes, whoa, you didn't define the function. Or maybe I defined it in the wrong place. Or maybe it's not, I have the header file but not anything else, or I can't find the actual function definition. These are linking errors, and that actually leads to weird, wacky things. They're actually harder to come by or harder to find because the ability to find a linking error is actually much harder for the compiler. Compile errors, it hits it right there. It's processing your code and figures out that something is wrong. Versus a linking error, it doesn't know why it's wrong. It just says something weird happened, essentially. And a runtime error things like when I go to run my code and I try and access a null pointer, for example, and I try and get index position 2 in a null pointer, right? Everything blows up when I run the code, not before, not when I'm compiling, but when I actually try and run the code, a runtime error. Um, and these can be really dangerous in the fact that you don't know you're going to have it. You may never actually hit the scenario when you get the runtime error. So, for example, I don't check if a pointer is null. And all of my testing, all the testing that we do with the code doesn't ever pass. You never test it with a null pointer. And then later on, somebody else, like an end user, ends up trying it with they do something that causes a null pointer to be passed into your function. You try to get an index position 3 in the null pointer, and everything explodes on them. That's a runtime error. Those are really terrible in the fact that sometimes you can't even tell that they're going to happen. You cannot necessarily predict that you're going to have runtime errors. Okay, so we've looked at a whole bunch of preprocessor directives. Things like include, that would be sort of like include .header files. I can define things. So, before I do this, I'm going to do this if def or if ndef approach to doing things as well. I can do if statements even, and that will remove chunks of code depending on a certain condition. It's not using that if statement, it is removing chunks of code whether a given condition is true. I can do an error message even. And we even looked at implicit and explicit casting. So we're gonna go now. I'm gonna keep this, and I'm gonna show you one last thing, which is I'm going to show you that preprocessor instruction with pixel image. I'm going to use, instead of pragma once, I'm going to use the other way. So by convention, I'm going to use if and def. If something is not defined, and I want to define pixel, by convention, I use underscores in between my individual words and an H at the end. So if pixel image H is not defined, define pixel image H. What's that going to do? It's going to, if it wasn't defined, I'm going to define it. And then at the very end, I'm going to put in a line of code that says and if. So if it wasn't defined, then I will define it. I should do it. And oh, it's an if and defined, and if. So I want to define if not defined, then I'll. Oh, it's already in there. It was, they've pre-filled it in. All right, here we go. Back down to the bottom. So if it wasn't defined, now I'm going to define it. That's why I was having problems here. Okay. Yes, I want to stop debugging. Nothing should have changed from my original Pragma once code and this. They are doing the exact same thing. That's what Pragma once is actually doing. It's doing this chunk right here. It's just this is the traditional old school way of doing, making sure that the header files are only included once. And here's Pragma once doing it a simpler way. All right. With that being said, I'm going to stop the video again, and next time around we're going to be looking at file I/O. Thanks everyone.